these ideas can be understood. First of all, are there any questions about anything? Yes?
I have a question pertaining to last lecture when you said waves are like waves, and then when they hit something, they hit like a particle.
Yes.
So when there are two waves, when they interact, do they act like a wave, or when they interact, do they act like a particle?
When they're interacting, if they haven't hit anything yet, they act like waves. So you can get interference. So you do get interference while they're traveling. And so that's why it's possible to get interference even with matter waves. So as long as they're traveling, they act like waves.
So even when they collide with each other, they're still waves? Or do they, like, in the moment of collision?
In the moment of collision, they act like particles. With some reservations. That is to say, you can sometimes treat them as though they have momentum, and all right. Let's see how some examples work out. We do have collisions of particles where they act like particles, but actually they're acting like waves as they're traveling. But then, in the moment of collision, they act like particles because they've been localized. By the way, I could add that on next Monday, the colloquium here is going to be on precisely this kind of wave-particle dichotomy. People are still worrying about that, and they're doing some experiments on it. And if you want to hang around after class at 4 o'clock on Monday, I would suggest staying maybe for the first 15 minutes because, they go off on a deep end after a while. But to get a feeling for, even to this day, since 1925, when this was first brought out, we still haven't quite got the answer of how to think about these things. So the Professor Siddiqui, who's here, is going to talk about his experiments trying to understand exactly this kind of thing, which I'll explain a little bit more in detail with some of the words he will use. I don't know his work particularly well, but I intend to listen to hear what they're thinking about these days. But to review briefly, we had the idea. Well, let me even go back even a step further. Let me illustrate something that I meant to do on one of the very first days. Is that visible enough? Way back even yonder? Okay. Now here is a very nice black body radiation applet. What one can do, if it's working properly, is you can change the temperature. It started out at a temperature of 5,000 degrees, which is roughly the temperature of the sun, and we can raise the temperature, and you'll see the two effects that we talked about. One is that the wavelength gets shorter. We have the Wien law, which is the wavelength at the maximum emission times the temperature is a constant. I'll even write down the value of that constant. It's around 3 times 10 to the minus 3 meters times Kelvin units, degrees Kelvin. That's meters in, because there's a length, meters, wavelength, and a temperature. So the units have to be that way. And the point is that as the temperature goes up, to keep that constant, the wavelength must get shorter. So that's what this is showing. Namely, if I go up in temperature, you'll see how the peak is moving to shorter wavelength. This is a wavelength scale. So if you go up to 7,000 Kelvin, you would get that. And here's the visible spectrum. So if the sun, for example, were at 7,000 Kelvin, we would have a pretty strong visible spectrum, but we'd get an awful lot of ultraviolet light coming from the sun, which would probably be bad for us. because the energy in an ultraviolet light is, by Einstein's equals h times f. The energy goes up with the frequency, hc over lambda. So as the wavelength gets smaller, the energy gets larger, and that's why you get a sunburn, for example, with ultraviolet light. When you put on a sunscreen, you're blocking ultraviolet, what is it, A and B? They have letters for that. The different A and B refers to various places on the spectrum. And that kind of energy is enough to do chemical reaction in your skin and change its color. Whereas down here, that's where you have tanning salons, where you go into it's obviously not very good because it's doing chemical reactions in your skin, and you don't want to do that, I would think, too much. Personally, I wouldn't like to. But see, two things are going to happen as you raise the temperature. There is this effect, the Wien law, and the other one is the Stefan-Boltzmann effect. And that is that the total energy under the curve radiated is proportional, well, to the fourth power of the temperature. It's very steep dependence on temperature. It goes up quite fast. There's also a constant here where that's usually written. So what you expect to see, and you can see it on this axis if your eyes are good, there's a unit 300 something times 10 to the 12th. As you go up in temperature, you'll actually go up to 200 and so on. In other words, the area under this curve is going to increase. Correspondingly, if I lower the temperature, you see the total area is getting less. The peak is shifting to higher, longer wavelengths. There, again, is about the temperature of the sun, and again, the colors or the radiation wavelengths that our eyes are good at seeing. If I lower the temperature even more, you see the scale of total energy is going down rather rapidly because this is exponential here. And if I go lower and lower and lower, now I'm getting down to around 2,000, 2,800. Now that's about the temperature that light bulbs, incandescent light bulbs, run at. So look what's happening in an incandescent light bulb. The visible part of the spectrum is this. This is the light we see. But most of the energy is way out here in the invisible infrared, so it's mostly wasted. That's why ordinary light bulbs are inefficient, because most of the energy that you put in, you don't see. And in fact, in some places now, I think in Australia or New Zealand, they've actually banned incandescent light bulbs. You can't even buy them there because they're so inefficient. They force people to use fluorescent lights or diodes, these, light-emitting diodes.
How is the blue LED different?
Well, the blue LED, yeah. The blue LED, LEDs are an entirely different kettle of fish. What they do, you put in electrical energy, and by a quantum effect, the quantum efficiency is much better, they emit strictly blue light. It's not like this. This is due to heat. See, this black body is in a sense, the whole black body is jiggling and with all its different wavelengths, and so it's radiating all over the frequency spectrum up to a certain maximum, more or less. The LEDs are, due to quantum effects, they radiate specific wavelengths. You can have a red LED or a green or blue. The blue LED, which won the Nobel Prize last year, has the advantage of the shortest wavelength, and it completes the red, green, blue spectrum to make white light. So if you wanted to make a white light for a room illumination, you would have a red laser and a green laser and a blue laser packed together, and you would your eye would see white. So, but this is a different kettle of fish. This thing here, because of the heat effect, it's all those thermal motions. So it's producing visible jiggling, and it's producing long wavelength thing at low temperatures. Now, that's already at 2,000. Now, this thing, well, it allows me actually to, let's see how far I can go do with the slider. Oh, okay. Wow, okay. I can get to 200 Kelvin. Well, let me try to get to room temperature, roughly 300. There we go. That's more or less room temperature. So what this means is that at room temperature, we are emitting radiation. The scale is way down. Where it was 10 to the 12th before, I read 10 to the 5th, roughly. So you're down 7 orders of magnitude in a total amount of emission. So we're not radiating much. And not only that, we're radiating at a wavelength where we don't see at all. So that's the room temperature. And this is a very important idea, which I will talk about next, I think. Yeah, let's follow up on this idea. Namely, that the sun radiates at one wavelength, broadly centered at one wavelength. We radiate broadly at another wavelength. So let me go back to this PowerPoint. Okay, now let me talk about a very interesting. So this is the black body radiation. Again, it's this thermally excited, necessarily statistical, necessarily jumpy kind of radiation with a broad spectrum thing. Now, which we more or less understand now. But let me just talk about something which is of current interest. Well, one thing of current interest is the idea that if you have this broad spectrum, again, depending on the temperature, you're more or less into the visible range. So at 2,000, you're just a little bit into the visible. At 2,500, quite a bit more. So that explains, for example, you've seen some new headlights on some of the newer cars. They're kind of bluish and very bright. Well, they figured out how to make headlights out of incandescent lamps, but can run at a higher temperature. So instead of running at around 2,000, they run it to about 2,500. And that makes quite a difference because you can get a lot more light, and it's also shifted more to the blue. So that's what's going on in those new headlights. The old headlights, if you turn the temperature up a lot, the filament would sort of melt, and it would evaporate. But they have figured out that if you put certain kinds of gases inside these new headlamps, the gases sort of recapture the tungsten and bring it back to the filament. And so you can run the filament at a higher temperature and get this bluish, brighter light with less power. So that's one thing. But more interesting, perhaps, is the idea that, well, here's the black body radiation corresponding to the temperature of the sun. And here's that spectrum that we saw. Now, the point being that, as I try to show you, at our temperature, say 300 Kelvin, we have a different spectrum coming out at a much different frequency, like 10 microns this is actually, or 1,000 nanometers. Okay, so what does that really mean? Well, here's a graph that shows both of those. Namely, here's the sun's radiation. Most of it gets through, this is what would radiate. This is the amount that actually gets through our atmosphere. Because the absorption in the atmosphere has a minimum, as I've mentioned before, it's a miraculous thing, that the gases in our atmosphere, oxygen and nitrogen and whatever, permit this radiation to get through. So the absorptions are high over here and over here, but miraculously, where the sun radiates is a window of transmission through our atmosphere, which is incredible. But then now I'm talking about the greenhouse effect. At the temperatures of our bodies and the temperature of the Earth, we radiate, well, a lot less, of course, very much less by T to the fourth, but in this spectrum range. And in this spectrum range, it turns out that the absorptions in the atmosphere are a lot greater. And there is just a window over here. But I just would point out to you that, in fact, I just got my electric bill yesterday, and I got a rebate because California has passed a law saying that if you save on greenhouse gases, they'll give you money, they'll lower your bill. So it was very nice this month. I have money, so if you want, well, I have money for cookies for later on. So that's the good thing. So thank California Energy Commission. So the question is, what are the greenhouse gases? And what are we saving? What can we save? And I find it very interesting because if you really look at what these gases are, of all these absorptions here, here's carbon dioxide. It absorbs here. So it cuts off this part of the radiation. See, the point is the Earth is radiating and the light is going back out space. Now, that's good. It's good and bad. It's good because it keeps the Earth warm after the sun goes down. I looked up just today the temperatures on the moon. Oh yeah. See, the moon has no atmosphere, but it's roughly in the same orbit as we are, and it's roughly the same Earth color. So what would you think the temperature difference between day and night on the moon is? The moon being heated during the day by the sun, and at night it cools down because it's not being heated. I was shocked, actually, to learn that during the day the moon goes up to 250 degrees Fahrenheit from the sun's radiation. Because, well, whatever. And at night, it goes down to minus 387 degrees Fahrenheit, 40 degrees above absolute zero at night. You know, that was the thing that when the astronauts go out into an orbit, if they're facing outside an extravehicular activity, when they go out tethered, one side is in the sunshine, the other side is in the shade. The difference in temperature must be tremendous, and that suit has to protect them against that kind of temperature. I find that amazing that they can make a suit like that. In any case, that would happen on the Earth if it were not for the atmosphere. In other words, this atmospheric blanket is modulating the temperature. It's keeping it from getting too hot and it's keeping it from getting too cold. So the greenhouse gases are good and bad. And so I go back to this story. What are the greenhouse gases? And again, I'm a skeptic, so I always ask questions about these things. This is the total, let's see, this is the total absorption of the atmosphere. Very high over here. Now, why is it high? Well, it looks to me like this is the major absorber, which is water vapor. Water vapor is the major absorber. And carbon dioxide is this. And the other one people talk about a lot is methane. It absorbs here and here. And they talk about we have to control the methane emissions and the carbon dioxide. So I think the message that I get, I don't know about you, is that it's a rather subtle thing. If they're talking about that the atmosphere may rise by 1 or 2 degrees centigrade, the fact that we don't freeze at night entirely or boil during the day is really because of these gases holding in the heat and not letting it get out entirely, and that's a good thing. And the effect of the carbon dioxide is maybe to change, like instead of going down to minus 300, we stay at around, like, what is it, 300 Kelvin. We stay at a reasonable temperature at night, 50 Fahrenheit, or something, whatever we get down here. And I think it's very interesting to look at this. I was a little surprised when I saw this and realized that water vapor is the most abundant greenhouse gas. And that we're not going to do much about because the planet is covered with water. So the calculation that the climate people do must be very subtle, because they're talking about a 1 or 2 degree change, which may be disastrous, like 5 degrees centigrade is disastrous. But it's a subtle balance between the water vapor and these additional gases that we're putting into the atmosphere. I just point that out to you as I thought it was an interesting thing. Now, the other effect that I wanted to expand on a little bit is the Einstein explanation of the photoelectric effect. Oop. My own computer is treating me badly here. Let me try this again. Microsoft reporting error. Let me. Ooh. What happened here? Now this is my computer acting up. So let's see if I can get those back. Well, maybe I don't even have to. Oh, yes, I do. I want to show something here. Yeah, I want to show that particle and waves thing again. Let me load it up again. What I wanted to point out to you is why perhaps these quantum effects were not noticed earlier. And that is the thing that the energy in the quantum is, well, that's not the one I want either. Sorry. Where is... Oh, here it is. Let's try this one. I wanted to show you another effect that comes out of something like the black body, and it sort of helps us appreciate it a little more. Well, first of all, let me make the... Let me make the point that what Planck actually envisioned was that in the walls of his black body, there are all kinds of oscillators of different frequencies, from low frequencies, maybe soft oscillations, to very high frequencies. And at each of those, whatever that oscillator was, whatever its frequency was, it will have multiples of energy states with the difference in energy equal to HF times the frequency of that oscillator, but you could have n of them, so that the second level here would have 2 HF, and the third level, well, it's 1 HF above the ground state, and the next level is 2 HFs above the ground state, and then 3, 4, 5, 6, et cetera, et cetera. So every oscillator has its sort of harmonics, higher frequencies of the same, higher energies of the same frequency. Could exist in 2 of these, or higher levels of this state. So that's how an oscillator gets more energy, but it gets it in steps. On the other hand, if you had a high frequency, its first level might be quite a bit higher than the 0th level. This would be 1 HF high. and then the next level would be here and here. So there'd be the energies of any level are n times hf. That was his picture. And again, the argument that he comes up with is that you have a certain amount of energy that you're putting in with thermal energy. And if the thermal energy is enough, it can excite these levels, maybe several levels of a low-frequency oscillator, but it's not able to excite a high-frequency oscillator because it doesn't have enough energy. So this oscillator here is frozen out, or starved of energy. Now, the same effect was understood by Einstein to apply to all periodic motions. There's the atmospheric, let me see. Oh, it's quitting again at that point. What's going on here? Oh, that's weird. Okay, well, let me go without that for the moment. What Einstein noted was that you could have other systems, if they had a periodic motion in them, that the same kind of phenomenon should be observable. And it was observed, in fact. It had been known, for example, that what's called the specific heat of a material, which is the amount of heat you have to put in to raise the temperature of something, that for all solids, it was pretty constant, and then at low temperatures, it would drop off. And Einstein said, I can explain this phenomenon too. This is a solid. I think in his paper, he actually had the data for diamond. Somebody had measured this, what kind of heat you have to put in to change the temperature of diamond by a certain amount. And Einstein said something like this: let me make a very simple model of a diamond. Namely, it has atoms, and they're attached by springs. Let me just imagine that there is some frequency of that this lattice vibrates at. And by Planck's idea, the energy needed to get that oscillator going is h times the frequency. Oh, I had wrote omega, which is 2 pi f. But let's keep calling it f. Yeah. F is the right thing to do. Either one. But anyhow, so this is a kind of argument that he made for now, not for light, but now he's talking about vibrations of a material. And so you have these energy levels, the first one being at h times f of this oscillating lattice, and this one at 2hf. And his argument was, if I have a high enough temperature, all of these, I put in heat, and the lattice absorbs it. This level absorbs some energy, and this oscillator also gets going, so I can absorb energy if the energy is higher than this characteristic frequency. So if I put in energy way up here, that energy being kB, the Boltzmann constant times temperature, if I put in that energy way up here, yes, these oscillators absorb the energy, and they start vibrating. On the other hand, if I put in too little energy way down here, a low temperature, although I'm offering energy, this oscillator can't take it because it needs at least this much to get going. So if I give it too little, it won't accept it. The oscillator doesn't get going, so it doesn't take up any heat. So by that, using that idea, he was able to explain why the amount of heat taken up by a lattice as you change its temperature goes down at low temperatures, this curve. And he, just using Planck's idea, he fitted that curve very nicely. So he used this idea to explain the specific heat. You'll see the similar thing in my notes. The specific heat of gas. For example, hydrogen gas, H2. If you do the same type of experiment, ask how much heat you have to put in to change the temperature, it does something like this, which is pretty weird. And the reason is that there are different frequencies. There's two different frequencies involved here. The hydrogen gas, H, is doing two things. It can vibrate, so that's one frequency, pretty high frequency, and it can rotate, rotational, and that's another periodicity. So what's happening here, so this represents one very high energy level. This is the sort of rotational, no, I'm sorry. The first one would be vibrational. And then you would have a second energy level, the rotational energy levels, which are lower, and you have multiple of them, like that. And that's it. That's what a diatomic molecule can do. It can either vibrate or tumble. That's pretty much it. So what he said is, as I lower if at a very high temperature, I can get the molecule to vibrate, and it will take up energy, take up heat, because it's exciting these vibrational modes. So that is the vibrational mode, taking up energy. If I lower the temperature too much, I don't have enough energy to start a vibration, so it doesn't the vibrations don't get started. It doesn't take up any energy into the vibration, so that the heat drops off. And then but I have enough energy to excite the rotations for a while. And then if I put in even less, if the temperature goes down even further, the rotations don't even get going. And it doesn't take up any energy. And so the specific heat looks like that. So in a stroke, you explain the black body, you explain the specific heats of solids and gases with the same idea. The idea that you need enough thermal energy to get the vibrations going. If you don't put enough thermal energy in, you freeze out those vibrations, and the system doesn't take up any energy there. So it doesn't take up any energy. It means it doesn't absorb any heat, or it doesn't radiate at those frequencies below which you have too little energy to get you going. Another thing that you can do very simply is to derive this law on a very simple basis. Maybe I'll leave this for you as an exercise. But on this kind of argument, you would say that the highest frequency that you could excite would be roughly when the thermal energy that you're putting in, namely this kB times the temperature, when that's roughly equal to the oscillator, the first oscillator energy difference, you will start to freeze this one out. So you would say, when very rough calculation, when kBT, that's the thermal energy, is less than a given oscillator's first frequency, when that happens, then F1, this F, will freeze out and stop oscillating and will stop radiating. And if you do that, well, let's just push that into this form here. This form is lambda times T. So, okay, so let me do kBT less than HF is equal to C over lambda. And then maybe I can do it here. Have enough room. So let me try to get into the form T. When T is less than HC over KB, and let me put the lambda on the other side. So here I have the same form. Lambda times T is equal to this, H, C, and KB, all of which are constants. So this is the form, very approximately, at which you would find the wavelength that's where the cutoff occurs. And if you put in the numbers, which come from a whole different world, namely take Planck's number, well, this comes from the black body. It's 6 times 10 to the minus 34, and C we know is 3 times 10 to the 8th meters per second. And this KB, now I usually don't remember that. I think it's more or less 1 times 10 to the minus 23 in units. Did I ever write that down? No, I think it's, let's see. Energy is KT. So K must be of units joules per Kelvin. Well, if you actually put in those numbers, you get something which is the same order of magnitude as this. So the whole thing holds together very nicely. Now, we have just a few more minutes. I wanted to move on to the next, although there's much interesting stuff here, I wanted to move on to understanding wave mechanics, which is the next chapter. And I want to summarize, I don't want to spend too much time on it, actually, in real life, but I wanted to give you the general picture of how to look at wave mechanics. And the real idea is that de Broglie said, and we demonstrated with that oscilloscope, that particles have a wave-like character. So finally, Schrödinger put together an equation for a wave. I've shown you the electromagnetic wave. It has an equation with derivatives. In other words, the spatial part is varying and the time part is varying, and that makes for a wave. So Schrödinger said, yes, there are waves, but the difference is that in an atom, the wave is kind of held. If the electron is a wave, it's being held by the nucleus. We know that from various experiments, and there was a theory by Bohr earlier in 1912 for the hydrogen atom, which worked pretty well. But when de Broglie came along with the idea that the electron is a wave, and de Broglie actually said the key step, namely that there's something special if the wave goes around, and if you have a wave that sort of comes back upon itself, sort of like if you have a string, a nice vibration of a string is when it just vibrates back and forth in one lobe, or it could vibrate like that. Something nice rather than junky, all over the place. These are the simple modes of a vibrating system. So Schrödinger said, okay, let's think of the simple modes of a vibrating system. Let me see if I have that here, finally. I think it killed off both of my PowerPoints for some reason. Because I have a quote from Schrödinger's first paper where he says, Bohr, Planck said that the energy levels are n times, integer times the frequency. And then Bohr came along and said that, moreover, you need another integer to explain the hydrogen atom in Bohr's simple model. And Schrödinger and de Broglie say, I can explain why you need simple integers, because what you're trying to get is like n half wavelengths, n being an integer, in a space. So what you're trying to do is fit a wave into a confined space, and that will give you integer solutions. And they could be quite complicated depending on this is very simple. This is just straight line and held at a certain distance. But suppose the thing is a spherical shape. You can get spherical waves, and they could have. So this is this cute demonstration which typifies what's going on in all waves, in particular our interest here is in atomic waves, particle waves. Now I hope, yeah, and what this is, it's just an audio speaker whose sound you can hear, a certain sound frequency. It is, I don't know, 0.68 something or others. Sounds pretty low, maybe that's 68 cycles. And it's a square plate. Can you see it pretty well? Square plate. And it's being shaped. Now, the plate it starts to vibrate in all kinds of modes, but it has to take up sort of the geometry of a square plate. If I had a circular plate, it would be different. And where there's sand that we put on here, too much. Now, where does the sand stay? The sand stays where the thing is not vibrating, sort of in the valleys, where it's not shaking. Of course, the vibrating parts shake the sand into the troughs. Okay, now the point that I want to make is that as I increase the frequency, the wavelength gets shorter, and various patterns can develop of the vibration. So let me try that, turning up the frequency with... here's my knob. Whoa, 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 whoa. You can hear the frequency going up, the pitch. I don't know why they're all going in the corner like that. Let me try putting some stuff over here. Now you'll see, let's see what happens. It's a little hard to predict, but you see how it's taking up the geometry of the square? It's compatible with that. And if you remember your chemistry, the shape of the S and P and D orbitals, they were all kind of funny looking shapes. See if I don't know why everything's drifting downhill here, I guess. Getting up there. Here we go. Another orbital pops in. So there are different higher energy frequencies. And look at that, isn't that a beauty? And so there's a bound state, and I'm increasing and it stays there because that's a steady state. There's another orbital. See, at a higher frequency, more nodes. Oh, that's beautiful, isn't it? It's good. It's getting to the painful range, and look at that. Yet a higher mode with a more complicated distribution, sort of like the d orbitals or the f orbitals of a thing. So it's trying to fit into the geometry, and it takes a different shape. As the frequency goes up, the wavelength gets shorter, and all these different marvelous patterns can develop. And that's exactly what's going on in the atom. It's just Schrödinger found that if you solve the waves in a confined space in an atom, you'll get these odd shapes. S orbitals, P's, we call them now D's, F's, G's, and all those. Or if you put it in a box, you'll have a certain set of shapes. Or if you put it in a bowl, you'll get a certain set of shapes. Let's see how far we can go with this before something bad happens. Let me try some more sand just for fun. This may be too much, but let's see what happens. I'm up to, I don't know, whatever this says, 1.8 something. It wants to do something. I hope something bad doesn't happen. Oh, it looks like it wants to do something. It looks like it wants a mode there. Oh. Ooh, that's a very interesting one. Here, right in there, there's a mode. Can you still hear that? I'm older than you, and my hearing is not it's cut off. Oh, look at that. Oh, that's very pretty. Can you still hear it?
Yes.
Really? Good for you. You know, I heard there was a story that some guy wanted to keep teenagers out of his store, and he played this sound, and his older customers couldn't hear it. But the teenagers were bugged, so we kept them out. That's a pretty one. Look at that. But you see, we're going to a way high frequency, and the wavelength is really short, and you're getting these very short wavelength modes in all kinds of patterns. Can you still hear it?
Yes.
Really? Good for you. That really would work. Well, all right, let me see if I can go beyond your hearing. Can you still hear it?
Yeah.
We've come to the edge of this box. All right, let's see what happens if you go back down, just for fun. Let's see if it restores itself. Well, you guys, I think you just did very well. I think we're up around 8, 9. I don't know exactly what that is. 9,000? No, it's got to be less than that. More than that. Oh, here I can start to hear again. Let's see if it restores it. We're going down. What I could do is put up the amplitude a little bit. Shake it harder. Ooh. Oh, that's pretty. So as you study the wave mechanics, realize that that's what basically we're doing. As you go up in these frequencies, you're going to get different shapes which are going to try to fit into the geometry or what they call the potential that you're dealt with. In other words, if you have a Coulomb potential, you'll get one set of shapes. If you have a harmonic potential, you get a different set of shapes. If you have a square potential, you get a different set of shapes. And they can get pretty exotic. Or you could have a periodic potential. You could have like an atom lattice. All right, there's a nice low frequency mode. Okay, anyway, I want to come and play with this. This is fun. Otherwise, have a good weekend.